So page 12 of your unit handout. This is a very important lesson. It's usually a long lesson. And given the shortened classes, I've done my best to shorten the lesson a bit and shorten how I present it a bit. But regardless, every time I teach this course, this is something we spend 2 days on. We usually spend the first day going through the lesson and maybe getting to a few problems to practice, and then tomorrow we practice. This forms a very important foundation for what's coming up. Okay? We're talking here about what are called identities, and today we're going to learn about what an identity is. We're going to learn that there are identities in trigonometry called reciprocal trigonometric identities, quotient trigonometric identities, and Pythagorean trigonometric identities. We are going to be verifying identities in a number of different ways. What I'm saying is we're going to be taking things that we know are identities and just convincing ourselves that they are truly identities, whatever that word identity means. And we're going to learn about that. It turns out that identities have non-permissible values of the variable, and there's a difference between an identity and an equation. So let's get going on this. As a warm-up, we're going to consider this equation 2x squared minus 23x plus 5 equals 77 minus 5x. And I'm deciding to shorten this lesson down a little bit to the point where I'm going to tell you I don't think you need to write everything down, okay? Especially in the warm-up. You can choose to write down what you want, but I want to keep things moving past the warm-up quickly, okay? Verify, equals 77 minus 5x. Is that an equation? Well, yeah, there's an equal sign. Anything with an equal sign is an equation. X equals 5 is an equation. 2 plus 3 equals 5 is an equation. Verify that this equation is true for x equals negative 3. Well, all we need to do, and this is so important in this unit, is we need to independently evaluate the left side and the right side at negative 3. We do not want to start rearranging this. We want to treat the left side and the right side separately. And I've already done this. I've put negative 3 in for x on the left side, and I get 92. So if you want, you can write this all down, or you can write nothing down, or you can write left side at negative 3 equals 92. I don't care. I think the math here is junior high-ish, isn't it? I just enter it with brackets. And if I put negative 3 into the other side, I get 92. So we have verified that this equation is true for that particular value of x. Capiche? Okay. B is asking the same type of question, but it's coming right out and asking you, is that true for x equals 12? In A, you were told it was true. You were just asked to verify it. So what are we going to do for x equals 12? Well, we're going to take that equation, and I've put it on the top right corner of the screen here, and we're going to put 12 in for x on the left and 12 in for x on the right. And I have no doubt that you have the skills to do so. And what you're going to get is 17 on the left, and you're going to get 17 on the right. So the answer to this question is yes. What we have discovered through me leading you is that those two values of x are values of x that make that equation true. C, is the equation true for all values of x? Well, that's a difficult thing to prove. If I told you that all swans are white, and you went around the world looking at swans and every swan you found was white, does that mean there isn't a different colored swan? No, it doesn't. You cannot prove a positive by using examples, and we're going to come back to that. But we can disprove something. If you can find one purple swan, then you have disproven the statement that all swans are white. If we can find one value of x that doesn't make this true, then the answer to this question is no. So what I've done, and this is a really good strategy in this unit, is I've put in for y1 the left side and for y2 the right side. And rather than looking at the graphs, which is a legitimate strategy, I'm just going to go to my tables. So when I look at my table, I discover that they're not equal everywhere. I mean, there's 12. I happen to have 12 in here for x, and they're both equal to 17. But at other values of x, they're not equal. So this is an equation that is not always true. So the answer to this question is yes. The answer to this question is no. It is not true for all values of x. If it's not true for one value of x, it's not true for all of them. Are you with me on that? Okay. So we have an equation that's true some of the time. By the way, that -3 and 12 are called solutions to that equation. They're values of x that make the equation true. Let's try a different one. So warm up number 2. What about this equation? We have x plus 5 quantity squared plus 37 is equal to x squared plus 10x plus 62. Is it an equation? Well, yeah, because there's an equal sign. Is it true when we use x equals -3? Again, we want to calculate the value of the equation on the left side and the right side separately from each other. And it turns out if I put -3 in for x, -3 plus 5 is 2, 2 squared is 4, 4 plus 37 gives you 41. What about the other side? Well, -3 squared plus 10 times -3 plus 62 also gives you 41. And you can feel free to enter that in your calculator to convince you, or you can have faith in me that I'm not going to lie to you. I'm telling you the truth, okay? So we have verified that the equation is true for -3. Is this equation true for 12? Well, again, we're going to calculate the right side and the left side separately. When I put 12 in, I'm going to have to take 12 plus 5 squared and add 37. And I happen to get 326. There's nothing significant about that number. That's just what it is. And if I put 12 in the other side, 12 squared plus 10 times 12 plus 62 is 326. Do you have a question, Noah? No. Okay. I thought I saw your hand. You're just moving. Sorry, you're the only one I saw motion with in the classroom, so I thought maybe you had a question. Is the equation true for all values of x? Well, I'm putting in x plus 5 quantity squared plus 37 for y1, and for y2 I'm putting the other side. And it doesn't matter what these particular values of x are. Apparently my table is set up to start at 0 and go up by 4. y1 and y2 are equal for these particular values of x. But maybe if we scroll down enough in my tables, we'll find a value of x where they're not equal. So all I can tell you at this point is it appears so. It appears to be true for all values of x. That is not a proof. You haven't proven it to me. Let me show you what the proof would look like, and if you want, you can write this down, but you don't have to. The proof would be to compare the two sides, and this is an important idea in this unit, to try to turn one side using rules of algebra into the other side. Or to try to turn the other side using rules of algebra into the first side. Or maybe to manipulate the left side and the right side separately from each other to make them equal to each other. I think it's obvious that it's simpler to take the left side here and do stuff to it, to try to turn it into the other side. And how many of you see that you're going to get x squared plus 10x plus 62? Because x plus 5 quantity squared is x plus 5 times x plus 5. And then we have plus 37. Do a little bit of grade 9 math here. X squared plus 10x plus 25 plus 37. Well, grade 9s would maybe go plus 5x plus 5x. And then we simplify that. Let me think. What's 25 plus 37? Oh, it's 62. And what we would do at this point if we were asked to prove that equation is always true is at the bottom we would say the left side is equal to the right side, so our job is done. Okay? So now, what's the deal with all this? An equation is a mathematical statement that equates two different looking algebraic expressions. An identity is a subgroup of an equation. All identities are equations, but not all equations are identities. In our warm-up, we had two equations. One of them is an identity. What an identity is an equation that's always true except for non-permissible values. And I need to discuss that with you. So an identity is an equation that is always true for permissible values. So for non-permissible values, we don't care about that. This is an identity. And if I wanted to prove this, I could take the left side and factor the numerator. And then cancel those two factors and be left with x plus 2. And then I could say, oh, left side equals right side if I were asked to prove it. By the way, we're not going to be proving these kinds of things. We're going to be proving trigonometric identities. But is this always true for every value of x? The answer is no. It's not true for x equals 2. Because when you put 2 in, that left side is not defined. So if I were to put into my graphing calculator for y1, in brackets x squared minus 4 divided by, in brackets, x minus 2, and then in for y2, x plus 2, and set my table up to start at -8 and go up by 1, just because I want it to be kind of a surprise. They're equal. They're equal, they're equal, they're equal, they're equal. They're not equal there. They're not equal at x equals 2. They're not the same thing. But an identity is something true for all values of x that you were allowed to use. And we're not allowed to use 2, so we don't care about that line. Capiche? Okay. All right. So, in our warm-up, was this equation an identity? No. This is not an identity. However, this one is. And we proved it, right? By foiling out x plus 5, quantity squared, and adding the 37. Do you get the idea behind what an identity is? Okay, a couple of quick illustrations here. That is an identity. Because if you were to square x plus 2, you're going to get the other side. This is not an identity. I mean, I hope you can see that x squared plus 2 is not the same thing as 3x. It's harder with trigonometry to decide whether they're the same. Because as we're going to see, trigonometric expressions can put on many different masks. They can look different but be the same. Is this an identity? Yes, because secant of x is defined to be the reciprocal of cosine. If I wanted to prove this, I would put a line here, and then I would go, oh, well, this is 1 over cos x, and I'd be done. You're not going to be asked to prove identities like that, okay? This is not an identity. Are there values of x that make this true? Yes. Pi over 3, 7 pi over 3, negative pi over 3. There's lots of them, but not every value of x makes it happen. All right. Let's get into some trig now. Consider this equation, sine of x equals cos of x times tan of x. What are the non-permissible values of x? So, whenever you're dealing with non-permissible values of trigonometric expressions in an equation or an identity, any denominator is not allowed to be 0. Okay. When you look up here, do you see any denominators in this equation? You don't, but there is a denominator. Tan of x is sine of x over cos of x. And that leads me to this question. How many of you see why cosine of x times tangent of x is always going to give you sine of x. It's because tangent is sine over cos, right? So what we want to do with this equation, I'm not proving anything just yet, I'm rewriting it. Using all sines and all cosines. And this is a very important strategy. And I see that I have cosine of x being a denominator, which means cosine of x is not allowed to be 0. So where is cosine of x 0? This is why the understanding of the unit circle is so important. Cosine of x is the x coordinate. It's 0 here and here on the unit circle, at the top of every rotation and the bottom of every rotation. So we can write here that I like to, for non-permissible values, I like to say x is not allowed to be. That way it's unambiguous. I'm saying very clearly that these are values that x is not allowed to be. X is not allowed to be pi over 2 plus multiples of pi. That should require very little explanation at this point in the course, because at pi over 2, which is the top where cosine is 0, making this undefined, and 3 pi over 2 at the bottom, doing the same thing, they are separated by a half a revolution, which is pi radians. Verify that the equation is true for 40 degrees. Put your calculator in degree mode. And find cosine of 40 degrees. It's that number. Find, left side, find sine of 40 degrees. It's that number. Right side, find cos of 40 degrees, tan of 40 degrees. Make sure you close the argument on the cosine. You get the same number. Done. Verify that this is true by looking at the graphs. So we're going to go into our graphing calculator and put sine of x on one side, that's y1. It's cos of x, tan of x on the other side, that's y2. I'm in degree mode, so I'm going to stay in degree mode. Okay? Except I meant to go zoom trig, of course. There's sine of x, and here comes cos of x, tan of x. But you can't see it, can you? So I want to show you something that might be helpful in you understanding something. I'm going to change the legend or the method in which this second one is graphed to the bouncy ball. And I want you to watch this carefully. That's sine of x, and here comes the second one. And there's this stutter, for lack of a better word, this kind of abrupt break in things in my graph attempting to draw a smooth curve, because that was where the non-permissible values were. It's getting up to that point, and then it goes, no, I can't graph that, and then it, bloop, and it moves past that point, and it continues in that fashion. So we're done. Any questions with that? All right, is the equation an identity? Well, yes, because we've verified it on the graphing calculator, but if we wanted to, we could use what we already know to be true. This, by the way, is a name, there's a name for that identity, but you already kind of know tangent of x is sine of x over cos of x. Because on the unit circle, tangent is the y over the x coordinate. The x coordinate I'm talking about not being this x. So tangent on the unit circle is the y coordinate over the x coordinate. Y is sine, x is cosine. Left side equals right side. This is not a level of proof that you would be asked to do. It's just too simple. So yes, it's an identity. It's true for all values of x that are permissible. All right, so here are all of your identities. You will want your formula sheet out whenever we're doing anything in this unit dealing with the remainder of this unit. These identities, which you already know, you've been given these, have a name. They are called the reciprocal identities, and you need to know the names of them. You need to know this is what they're called. But that's not hard, because when you look at them, they contain reciprocals. These are true for any permissible value of theta. These are called the quotient identities, and we haven't learned these, but we have kind of. Because you know that tangent of theta is y over x, and on the unit circle, sine of theta is y and cos of theta is x. So this is an identity. Tangent of theta equals sine of theta over cos of theta. It's always true as long as theta is permissible. Since cotangent is the reciprocal of tangent, cotangent of theta would be cos of theta over sine of theta. These are called the quotient identities because they are a quotient. A quotient is a fraction. It's the result of division. And then we have these three identities which are called Pythagorean. And they're Pythagorean because they come about by using a right triangle on the unit circle somewhere. Okay, and we don't need to get into that. The Pythagorean identities all contain the number 1 and squares of two other trig ratios. This first one, you should know. I don't know that I've ever written it that way, but we've said y squared plus x squared equals 1 when we talk about the unit circle. And when we talk about the unit circle, y is sine of theta and x is cos of theta. So that's why that's true. And then we have the other, so you can recognize the Pythagorean identities, and they're all on your formula sheet. So if you want to add these names, that's fine. So what the bulk of the remainder of this unit is about is using these identities and your algebra skills to solve problems. Okay? And it's going to require a lot of practice to become familiar with the identities and to get better at working with identities in general. Let's take a look at the examples continued. Verify that this identity is true for the following values of x. 300 degrees. So I've already done this. I've just loaded it up here. You could do it yourself. You're going to get 1. To verify means to put the numbers in and calculate. Verify that it's true for 5 pi over 6. Well, what is sine of 5 pi over 6? Like everybody, I like that when I say that, everybody's going, some people are doing this, they're looking up, some people are doing this, people turn their head a little bit. I hope you're visualizing the unit circle and you're saying 5 pi over 6 is in this location, and I'm after the y coordinate, which is 1/2. So this is 1/2 squared. What is the cosine of 5 pi over 6? Negative root 3 over 2. Squared. So what do we get? 1/4 plus 3/4. The square of negative square root of 3 is positive 3. And the square of 2 is 4. So we're left with 1/4 plus 3/4, which is 1. Prove, so we have a lesson down the road about a week from now on proving identities. But I like to, in all of these lessons leading up to it, every now and then throw in a proof. You were asked to prove this identity using other identities. So what you do is you write the left side and the right side separated, and don't put equals. You cannot start a proof by saying equals because we're trying to figure out that it's equal. We're trying to prove that. I always just like to draw a vertical line down the center. So here's what we're going to do. I am going to write this as 1 plus sine squared of theta over cos squared of theta. Why am I allowed to do that? Because I know that tangent of theta is sine of theta over cos of theta. So tan squared would be sine squared of theta over cos squared of theta. Here's what I want you to do when you're doing a proof. Whenever you use a known identity in your proof, write down the name of the identity. So what I'm going to write here is that we just used a quotient identity. And the thing that you need to work on is being organized. Those of you that are, this is not a criticism, you're chaotic in your thinking. You have so many things going on that you write stuff here and you write stuff there and then you draw arrows. You do not want to do that with a proof. You want to keep things organized. You want to leave a little bit of room here so you can write the reasons, and you want to space things out and be very linear in your thinking, or linear in your expression of what you're thinking. If you do not remember the name of the identity that you used, a brilliant thing is to write this. You can just write down the identity that you just used. In other words, when you use an identity to proceed in your proof, you need to justify by saying which identity it is or naming the type of identity. So now what we are going to do is put these together with a common denominator. When you look at the right side, we're keeping our eyes peeled on the right side because that's what we want to turn this into. The right side is just a single term. It's not two things added together. So I need to write this with a common denominator. And the common denominator would be cosine squared of theta. So I need to take this number 1 over 1 and multiply top and bottom by cos squared of theta so I get a common denominator. And close to 30 years probably, every time I teach trigonometric identities, I get to this stage where I ask the following question, and I'm going to ask it. How many of you see how that's going to turn in to the right-hand side? When I ask that same type of question at the end of the class, more people should answer, I see it. When I ask that question tomorrow, even more people should see it. When I ask it next week, even more people should see it. So what your goal is to always get better than you were before. And I say that because this whole process that we're entering into can be frustrating. And you need to understand that it's going to take time. Well, I have a common denominator here now, and I can put them together. I'll ask the question again. How many of you now see, I'll give you a second to write that down. How many of you now see, and you didn't a minute ago, how this is going to become the other side, which I'm just going to write here as secant squared of theta. How many of you see how that's going to become secant squared of theta now? Why is this 1 over cosine squared of theta? How did I go from this to this? Because cos squared plus sine squared is 1. And you will remember that. I've had a student that comes and talks to me. He came in a couple of years ago, and he came into my class in the middle of a lesson. I hadn't taught him over 25 years, and he said, oh, cos squared plus sine squared equals 1. He remembered it, and you will as well. And he hasn't been doing math for 25 years. He's an electrician. He's doing a different kind of math. So what do I put here? I put Pythagorean identity. So you guys still with me here? Do you agree that these two things are equal, left and right? But we're not done, because they are not equal on paper yet. You can either choose to write here 1 over cos squared of theta and write reciprocal trig identity, or over here on the left, write secant squared of theta. But you have to have them written identical for the proof to be complete. You can't just go, well, that's obvious. So I'm going to put secant squared theta because of a reciprocal identity. And now we can put left side equals right side. And that's the whole goal of a proof. So this lesson is not about proofs, but there's one so that later on when we get into them a little deeper, you'll know what we're talking about. This is why on the front of your handout I have this kind of meme or whatever you want to call it. I don't always replace everything with sines and cosines, but when I do, it almost always helps. So I'm going to give you a handout here in a little bit that says when simplifying trig expressions, try these things. And the first thing is replace everything with sine and cosine. For each of the following, use known identities to simplify it. So now we're kind of in the final stretch, the home stretch here. How many of you see that this is equal to sine squared of theta or sine squared of x? Well, what's the first strategy we should do? In fact, I think I'm going to give you this piece of paper right now. Try replacing all ratios with sines and cosines. If anything's going to work, it will be this more often than anything else. Now, how many of you see that this is going to be sine squared of x? It's almost obvious. I mean, I don't even think I would give this to you as an exam question. But we're building up to something here. We are not proving anything we do not need to justify. All you need to do is say that tan is sine squared, and the variable is x, over cos squared, multiplied by cos squared of x. Look, and I'm not saying this because I'm proud of my work, but look how neat the cos squared of x is for the second part. It's on the top, so that later if I have to consider a fraction, fractions are kind of lined up, right? We don't have to do that. We know from our rational expressions work in Math 20 that you can cancel a factor on the top with a factor on the bottom. So this is equal to sine squared of x. If you take a look at this one, it says if you have fractions being added or subtracted, bring them together with a common denominator. That's what we did in that other question, where we had 1 plus, I think it was sine squared over cos squared. We're done. Okay, well, let's write everything in terms of sines and cosines. Cosecant is 1 over sine of theta. Secant of theta is 1 over cosine of theta. Cotangent of theta is cos of theta is cosine of theta over sine of theta. And we'll just double check all of those. Is cosecant 1 over sine? Yes. Is secant 1 over cos? Yes. So how do we handle this? Well, this is why whenever it comes up in my math classes where you can cross multiply or you're dividing fractions and you have these rules of maybe multiplying by the reciprocal, I tell you, don't do that. What you want to do is consider that this is what we call a complex fraction. It is complex because there is a big numerator over a big denominator, but in the numerator, there is a denominator. There are multiple denominators in the numerator. In the denominator, there's a denominator. We do not want denominators within numerators or denominators within denominators. So how do we get rid of them? We multiply the top and the bottom of this entire fraction by whatever we need to eliminate those denominators. So for example, if I multiply the bottom of this equation by sine of theta, that would cancel with the sine of theta I've highlighted, but I also need to multiply the top by sine of theta. what I'm doing is I'm multiplying the top and the bottom by the same thing, which means the fraction is being multiplied by 1. Will that clear all of the denominators? No, I still have the cos of theta. So to get rid of that pesky cosine of theta, I need to do the same thing with it. And now I focus my attention on the top. Well, I'll just ask this question. How many of you see, I'm going to go out on a limb here, that this is secant squared of theta? How many of you see that it's 1 over cos squared of theta? After all the canceling is said and done, cos cancels with cos, sine cancels with sine. So on the top, all we are left with is 1. And on the bottom, what happens is the sine cancels with the sine, and we are left with a cosine times a cosine, which is cosine squared of theta, and we can write that as secant squared of theta. So who knew, and that's not a question I want you to answer, that that thing is equal to secant squared? You can't tell by looking at it. One thing I need to mention here is notice that I'm working down. I really hope that you've broken a habit that you might have had, which is to go equals, 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 and left to right. Do not do that here. It's wrong, okay? It's a bad move. Cosecant squared of theta minus cotan squared of theta. Well, we could try replacing everything with sines or cosines. But look at the second note. Remember to keep an eye out for parts of any known or familiar identities. As soon as I see a squared, I'm going to look at my Pythagorean identities. Okay, so for example, I know, and I never remember them after being away from this for a few months. I know that there is, I'm going to go on a limb and say that, I don't know. There is a trigonometric identity with cotangent squared of theta, correct? Georgia, can you help me out and tell me what it is?
1 plus cotangent squared of theta equals
Equals cosecant. So are we in agreement that's the identity? Okay. So how can we use this? Well, you know what I could do? I could put in here 1 plus cotangent squared of theta. Because cosecant squared of theta is 1 plus cotangent squared of theta. This is the quick way to get there. So if I put in 1 plus cotan squared of theta, and then I subtract this cotan squared of theta, this is equal to 1. Any questions with that one? Well, you know, I think we're going to be dealing with point 1 here, replacing everything with sines and cosines. And if you have fractions, bring them together. Because as soon as we change things to fractional form, we're going to have, as soon as we change things to sine and cosine, we're going to have fractions. I hope everybody sees what I've just done there. Already you're becoming more comfortable with tan of theta being sine over cos. So that means that I want a common denominator. The common denominator will be cosine of theta. And there's no need for us to keep writing sine of theta, it's sine squared. Which means I have to take this cos of theta over 1 and multiply the top and the bottom by cos of theta. I want to get the same denominator so I can put them together. That's where all the magic happens, when you get a single fraction. How many of you see this is going to be secant of theta? Not yet? A couple of you, yes. Why? Because this is all now over cos of theta, and the top is cos squared of theta plus sine squared of theta. And you should know cos squared plus sine squared is 1, like you should know 2 plus 3 is 5. The numerator of this is 1 because of what I call the famous Pythagorean identity relating sine and cosine of angles. So this is 1 over cosine, which is going to give you, if you want to write it as a single trig ratio, it's going to give you secant of theta. Either one of these is acceptable. Let's try another one. Well, there's nothing you can do here other than put these together with a common denominator. Right? Everything's already written in terms of sine and cosine. I don't recognize anything in there. It's not like I'm looking and seeing cos squared of theta plus sine squared of theta. I don't see that. So the common denominator would have to be that. I mean, this is like having rational expressions where one of your denominators is x and the other one is x plus 5. Your common denominator would be x times x plus 5. So I need to multiply the top and the bottom of this by sine of x. Whether you choose to put that up there or not is up to you. But when I multiply the top and the bottom by sine of x, what I get is sine squared of x. I need to multiply top and bottom of this one by 1 plus cos x. So on the top, I'm going to have cos x times 1 plus cos x. I'm multiplying top and bottom of the first fraction by sine of x, top and bottom of the second by 1 plus cos of x. Now, when we put these together, it's very important for you not to expand the denominator. Why? Why do we want to leave the denominator in factored form? Does anybody know? Well, let's come back to that. You know, this is all about rational expressions, and if I had my way, we could throw out 2 or 3 units from Math 20-1 and just teach a whole bunch of rational expressions in algebra. It's so much more important. Sequences and series, who cares? Reciprocal functions, doesn't matter. This is very important. Let's write the top now as sine squared of x plus, I'm going to expand out the numerator. And when I do, I get cos of x plus cos squared of x. Are you with me on that move? Okay. How many of you see this is going to be cosecant of x? That this is going to be cosecant of x. I'll give you a minute to think about this. You do? Why?
Because the sine squared plus cosine squared is 1.
Okay, I'm going to pause there. Oh, I'm going to pause you there. Because this plus this, not what I wanted to do, that's okay, is 1. Okay? So what? Hold on. Now what?
So now you have 1 plus cos of x on the top and 1 plus cos x on the bottom, and those are both factors, so they cancel.
See, this is why we don't want to multiply out the denominator, because our hope is, since it's already in factored form, one of those factors, maybe all of those factors, will cancel once we expand the numerator, simplify it, and factor it if necessary. We didn't need to factor anything here. We just used that identity. So now we have a factor in the top and a factor in the bottom. And this is going to be something I will come back to again and again and again. You cannot cancel something unless it is a factor in both the numerator and denominator. And that means it is something that is written in brackets multiplied by other stuff that's written in brackets. So if you have, you want to see that vein in my forehead start to pop? Do that. You cannot do that. Cos of x is not a factor of the top. It is a factor of the bottom, but it's not a factor of the top. It's not allowed. Okay? So this is 1 over sine of x, which we can write as cosecant of x.